Now we need to talk about motor units. We've talked about the individual structure of the skeletal muscle and how the skeletal muscle is made up of multiple repeating units. And we did talk about what happens at the area where you have a nerve come down and articulate or come close to muscles. And so now we are talking about kind of the same thing, units of fascicles being controlled by a nerve, but we're calling it a slightly different thing because we're looking at it from a different perspective. So motor units exist in skeletal muscles, and they exist in skeletal muscles and operate all together, just like everything else that we've talked about. They contract at the same time, but what happens is there's kind of a unique property with regard to skeletal muscles because we don't want our muscles to fatigue. We want our muscles to be there and work for us when we need them. And for the most part, we need our skeletal muscles all the time, except for when we're sleeping. And even when we're sleeping, we need them because we turn in the bed, etc. So you have, with regard to a motor unit, you have multiple fibers that are innervated by the same neuron, but that innervation is, I would say, different. They're stimulated in different ways. And that stimulation in different ways, and it's actually activation levels. They're stimulated at different activation levels. And that is purposeful. It's to almost give this muscle the ability to recoup while it's still contracting. So you have the muscle contracting as a unit, but not all fascicles are contracting every single time that muscle contracts as a unit, on average. And so with regard to a motor unit, you can have a muscle like the bicep, which can be innervated by, say, just one or a couple of neurons, or you can have muscles, so depending on the level and sophistication of movement that needs to be produced, if you compare the movement that the bicep does, which is pretty simple and you just have basically one type of movement, compared to all the various movements that your hand can do, there's a difference in the number of neurons that are involved in activating those muscles. So any specific muscle group is going to have one neuron, but there may be just a few fascicles for that neuron to look at if you're looking at the muscles that move the hands, and also actually the muscles that move the feet. The feet are very subtle in their movement also. And then the other thing about these motor units is, so say you have a wonderful thing going on where you have some contracting and some in their recovery period. Well, if it just so happens that you need more, a bigger burst of strength, those that are in their recovery period, as long as they're able to accept a new stimulation, so as long as they're not in a period where they can't accept stimulation at all, they can be recruited. And so what you can have is a more forceful contraction based on how many motor units actually are stimulated by need. But just generally, when you are exercising, or you are walking, or you are standing upright, or you are lifting your textbook, there's a finite amount of motor units that are portions in that motor unit that get stimulated at any given time. And so that's why you have this coloration here, and the key on the unit 1, 2, and 3. That's kind of arbitrary. They're just using this as a representation of what happens. Muscle tone is something that we've talked about this a little bit already. Muscle tone is the normal tension and firmness of the muscle at rest. So the normal tension and firmness of your muscles when you're just sitting there or when you're laying down. Not when you're upright, not when you are at attention, just when you're at rest. And then what happens is, with regard to the recruitment of muscles, they can actually tense up without creating motion, or they can stay fairly relaxed without creating motion. But the more more tone you have in your body, or the more tone you're using at that particular time, the more metabolic activity your muscles are going through. In terms of recruitment of motor units, you have certain types of contractions. You have isotonic contractions and isometric contractions. And with isotonic contractions, you have a skeletal muscle changing in length and resulting in motion. So isotonic, the muscle changes in length and it results in motion. In isometric, the skeletal muscle develops tension, but the length is prevented, and so there's no motion. And you see that picture here. At the top of the picture is the isometric. You have a contraction, because you can see that muscle is creating that muscle belly, that bumpish in the artist's rendition, but there's no movement. So there's actually a tension of the muscle. That's what I mean by the bumpish. Tension of the muscle, no movement. And then the bottom two are the isotonic reactions, and with that you have the concentric phase of the contraction, and with the concentric phase of the contraction you have a shortening of the muscle, and you have the muscle shortens, and you have resistance over the load. So the muscle shortens, you have resistance over the load. With the eccentric phase of the isotonic contraction, the muscle actually lengthens. Both phases you have movement, but in the concentric, the muscle shortens and you have movement, and the eccentric, the muscle lengthens and you have movement. In isometric, there is tension created but no movement, no change in length. Some of the stuff we have to finish up is more housekeeping. So not housekeeping, but defining terms in a little bit more depth than just one or two sentences. So with that contraction of the muscle, of the motor unit, there is a formula that the amount of your load is going to be inversely proportional to the speed with which you can lift that load. And that actually is more of a mouthful than it should be. The heavier something is, the slower it's going to be to lift it. So if you have something that, a piece of paper, you're going to lift a heck of a lot faster than, say, a brick off the table. So that's the relationship of load and speed. And then speaking of muscle fatigue, muscles use ATP, and ATP is made in that Krebs cycle that we kind of talked about when we talked about the cell, the Krebs cycle, where you have a 6-ring carbon cut in half, put in the cycle in the mitochondria. That creates ATP. It can create ATP without oxygen and with oxygen. So there can be an anaerobic production of oxygen and an aerobic production of oxygen. The aerobic production of oxygen that takes place in the aerobic production of ATP that takes place in the mitochondria, the anaerobic production of ATP that takes place in the outer portion of the mitochondria can both happen, and they both result in ATP, and that's what your muscle needs to create a contraction. But what happens is with anaerobic production of ATP, there is a byproduct, and that byproduct is lactic acid. That lactic acid is disassociates when it gets into the extracellular fluid, and that can cause an increase in pH. So that can cause not an increase in pH, but the pH to become more acidic with the hydrogen ions. That's the low pH with the acidic acid. So that can be one cause of muscle fatigue. Another cause of muscle fatigue is that ATP can't even be produced. So you have metabolic reserves and depleted. ATP can only be produced as quick as we have oxygen to create it, as we have nutrients to create it, and as quick as the mitochondria can create it. But if in fact that is overwhelmed, then you have metabolic reserves. You can also damage the portion of the cell of the muscle fiber, the sarcolemma, the sarcoplasmic reticulum, basically in the fact that you don't have this ability for calcium to come in, open up the bonding sites between the thin and thick filaments, and that can also lead to fatigue. Fatigue can be something that is it can be an umbrella of severity, and generally leads to exhaustion and many times pain if in fact you have damaged any part of the muscle. So if you've damaged any part of the muscle, you're going to have pain. With regard to recovery period, this is, as it says, it's the time it's required to recover after an exertion for muscles to return to normal. And it depends on the level of exertion and in terms of how long the recovery period will need to take place. So basically the recovery period is dependent on fatigue, dependent on what the muscle actually did, and what has to be reversed as a result of that that activation or that active time of the muscle. Oxygen debt, if you have overwhelmed the ability for the mitochondria to take oxygen in, use it to make ATP, you have oxygen debt. Then you're going to go into the anaerobic phase, which is where you have these, you get these byproducts that are potentially harmful to the muscle, but the oxygen debt is what needs to be replenished via a heavier breathing, faster breathing, and also relaxation. One of the functions of the muscle is heat production, and even when you're not shivering, I know I use that because it's graphic, you can see that in your head. Muscles aren't very efficient, which is unusual for the body. The body is usually very, very efficient. But up to 70% of the energy that is produced is lost as heat. And that raises the body temperature, and that can be a very, very good thing if your core needs to be raised, but can be a not necessarily a bad thing, but a thing that needs to be mitigated, I guess, by making sure the heat that is produced by the muscle then is taken by the blood to the surface and then dissipates out into the environment. And you do see this if you have somebody, if you see somebody who's exercising, they will start sweating more so. That's to control body temperature. Generally, you'll have more of a kind of a rosy vascularization. You kind of have a rosy look to the skin. That's because the blood has come more to the surface to allow the heat to dissipate from muscle exertion and to burn off or to get rid of that heat that the muscles have produced just as part of their functioning, but being somewhat inefficient in their functioning. And we will move on to the next one.